Thank you for the invitation. So today I will talk some progress um, for our study on the activity of nucleus, mainly the 327 compound. Okay, so here's the progress I will introduce today. And we have posted the papers on archive. Here is the related papers. The first one is the activity in monolayer-trilayer 327 compound. And the second part is the enhanced superconductivity in neodymium and samarium doped bilayer 327 compound. And then the third part is the structure corresponding to the superconducting state of the bilayer 327 compound. Okay. So let's move to the first part. So here's the introduction of the background. So for nucleus, there are different systems. One big family is the 112. It's the interlayer systems. The second family is the Robertson-Popper phases. So I think several other speakers will talk about the interlayer systems and also Robertson-Popper phases thin film samples. So today I will focus on the pressurized activity on the Robertson-Popper phases and mainly this 327 compound. As you can see here, for this 327 compound, there are two structures. One is the bilayer structure. Another one is this so-called 1313 structure. They have different stacking sequence. Okay, so after the discovery of the activity on this 327 compound, this bilayer compound, at that time, many groups working on RP nucleus, and at some time, people question, what's the region of the 80 Kelvin activity, because there are always some stacking force on this RP nucleus. For example, this 1313 phase, they have the same chemical formula. And in this work, they even see a drop at 80 Kelvin on this 1313 phase. So, which is the real superconducting phase corresponding to this 80 Kelvin superconductivity. But soon after, this work, many other works published, and they all demonstrate the 80 Kelvin superconductivity is originated from this bilayer phase. Okay, but whether this 1313 phase is a superconducting phase, and if it is, then what's the superconducting transition temperature? It's an open question. So our group, used lots of time to grow high quality 1313 single crystals, use high pressure flexible furnace. Here's our single crystal, and this is a schematic of the structure. So we can test the structure by XRD, by Raman, by LoRa, and the TM. All the measurements confirm our single crystal is this 1313 phase. Okay, so we can clearly distinguish the structure by all the techniques. But we can always ask whether it's a pure 1313 phase or it's only a small region with this phase. As you can see from this XRD measurements, this is the bilayer phase, so we couldn't see the bilayer phase. And we can use the TM to scan a very large scale. This is 20 nanometer. They all this 1313 phase. That means our sample is a pure phase, and it's a very high quality. Okay, on this sample, we conducted transport measurements. This is the measurements at ambient pressure. The resistance goes up at below 185 Kelvin, and when we apply pressure, it becomes metallic. When the pressure above 20 gigapascals, we see a clearly drop on resistance. indicating the emergence of superconductivity. If we zoom in this low temperature region, and we find this drop on resistance is at around 3.5 Kelvin. Okay, when we apply pressure, magnetic field at this pressure, we can see the drop was suppressed, indicating that that is superconductivity. Okay, here's the fading of the upper critical field. But as you can see here, the resistance, there's only a small drop. Okay, so we repeated the measurements on another piece of single crystal. Okay, so here is the measurements at a low temperature, a low pressure. We see some anomalies on resistance, and as you can see here, we see perfect zero resistance. Okay, the transition temperature is at 3.6 Kelvin. When we apply magnetic field, the superconductivity is suppressed. The upper critical field is at 1 Tesla. Okay, so that means it is indeed a real superconducting transition, but the transition temperature is quite low. We also measure the structure and high pressure. Here's the measurement by synchrotron X-ray diffraction, and under high pressure there's a structure transition. You can see here at low pressure the two peaks are separated, but as we increase the pressure, they merge together, indicating a structure transition. Here's the lattice constant, and the structure transition happens at 13 gigapascals. Okay, but the data quality is not very good, so we repeated the measurements by Raman scattering. With Raman scattering, we can see different phonon branches. Okay, if there's a structure transition, we can also determine the pressure for the structure transition. So this is the wave number of the phonons, and we can also see there's a structure transition appears at 13 gigapascals. This structure transition, corresponding to orthorhombic to tetrahedral transition. Because even at a low temperature or ambient pressure, the angle along c-axis, nickel oxygen nickel, is already 180 degrees, but A is not equal to B. When we apply pressure, the A will become equal to B. Okay, so that's the structure transition. We need to notice the structure transition appears at 13 gigapascals, but the superconductivity appears around 20 gigapascals. That means the structure transition is separated with the emergence of superconductivity. Okay, so here's the phase diagram. It's very interesting if we compare, the upper critical field, this HC2 over TC. Okay, for this bilayer phase, it's at this value more than 1. For the trilayer phase, it's also more than 1. Okay, but for this 1,2,1,2 phase and the 1,3,1,3 phase, this value is only half or below half. That means the superconductivity for the hybrid phase is very fragile, and actually, so we can claim the single nickel oxygen 6 layer is insulating. It's not superconducting. Okay, only the bilayer phase or trilayer phase is superconducting. Okay, so now we know the superconductivity on different in different Raphson proper phase nucleus. For the bilayer phase, it's 80 Kelvin. For this trilayer phase, it's 30 Kelvin. This 1,2,1,2 phase is more than 60 Kelvin. For this one, 1,3,1,3 phase is only 3.6 Kelvin. So we want to know what's the governing features for the emergence of superconductivity and how to increase the transition temperature. It seems the bilayer phase is very suitable for searching for high temperature superconductivity. So we doped neodymium and samarium to this compound. Okay, so when we doped samarium, we can decrease the C lattice constant. Okay, so this is C and this is B, this is A. So B is almost a constant. A decreases a little bit, but not too much. But the sample with more samarium doping, the sample will become more insulating, okay, even at ambient pressure. So after 50%, we couldn't, we couldn't successfully dope samarium. Okay, so there's a limitation for doping. Then we measured the structure transition under high pressure and transport measurements under high pressure. We found that the transition temperature for subactivity is increased. Okay, for example, for 50% samarium doping, the transition temperature is at 88 Kelvin. And for this measurements is 89, around 90 Kelvin. It's the transition temperature is increased 10 Kelvin. Okay, if we compare the neodymium doping, neodymium, the radius for neodymium is larger than samarium. So the decrease of C lattice constant is lower, but we can dope more neodymium to less than size. Okay, so we can dope 80%. Here's the C lattice constant. Okay, this is again is a B lattice constant, and this one is A lattice constant. So the most change for structure is the C lattice constant, and we can also we also found the spin density wave transition for the neodymium doped compound is enhanced. For example, as a function of doping, the transition for spin density wave is enhanced from 140 Kelvin to 160 Kelvin. Okay, so those data are those transition temperature are obtained from the resistance measurements. Okay, we from the derivative of the resistance measurements, we can see a drop at different temperatures. Okay, so for example here, for 80% doping, the spin density wave transition temperature is at 160 Kelvin. The higher transition temperature for spin density wave means the stronger magnetic exchange couplings. When we measure the subactivity under high pressure, we found that the TC is enhanced to around 93 Kelvin. Okay, so they are for different compound and different pressures. Okay, so our collaborators, Dimitri Simek, he used another technique, a so-called radio frequency transmission technique, to measure subactivity under high pressure. They have successfully used this technique to measure the subactivity for hydrogen-rich materials under extremely high pressure. Okay, there's a paper on arXiv, so I will not go to details on the technique. But for the measurements on our sample, this is a 70% doping, neodymium doping. The TC is at 97 Kelvin. For 80% doping, the on-site TC is at 98 Kelvin. Okay, so as a comparison to this cuprates, okay, this BSCCO, the transition temperature is at 94 Kelvin, and here's the analytical plot for the measurements. Is the transition temperature for neodymium doped nucleus is at 98 Kelvin. So, but the temperature is higher than transport measurements. That means the samples is not homogeneous, and some part of the sample has higher transition temperatures, and the maximum transition temperature is close to 100 Kelvin. Okay, if we plot the transition temperature as a function of in-plane lattice constant and C lattice constant, we found the TC has a linear relationship with the C lattice constant. Okay, so the data in this part, okay, is from thin film samples. They all follow the same trend. Okay, So that means a simple conclusion is that the interlayer coupling enhances the superconductivity in RP nucleus, and the slope is minus 28 Kelvin per angstrom. But if we look at the lattice constant for in plane, the box sample do not have the same slope with thin film samples. So we think the interlayer coupling is more important for the transition temperatures for the RP nucleus. Okay, I will quickly introduce the last part, the structure corresponding to superconductivity of the bilayer nucleus. So here is the phase diagram for the bilayer 327 compound under high pressure. There is a sharp enhancement of the superconductivity under high pressure. So if we simply look at this phase diagram, so we can see something must happen here. If we study the structure transition, at the beginning we claim there's a structure transition from AMAM to FMM. The difference is the angle along the c-axis from 168 degree to 180 degree. Okay, but it's still orthorhombic. Later on, our collaborators they measure the sample with synchronized diffraction. They claim the tetragonal structure corresponds to the superconducting state. And for this work from Jingguang Cheng's work group, they also claim there's the orthorhombic to tetragonal structure transition at high pressure. But for our work, in this paper, even in the superconducting state, we can still see the splitting of the two peaks. That means in this region, it's still orthorhombic structure. And in this work from Xianhui Chen's group, they also found that there are splitting for the peaks in the superconducting state. So there are many conflict results. And we measured our sample with Raman. Okay, with Raman scattering, we see at different pressures, we see a dramatic change for the spectrum above 14 gigapascals. Okay, that's the pressure where the superconductivity emerges. So if we analyze the Raman spectrum carefully, actually we found there are two-step structure transitions. The one is from orthorhombic AMAM to FMM. Okay, so for this structure transition, the angle changed from 168 degree to 180 degree. And another step is from orthorhombic to tetragonal. Okay, so in the superconducting state, when the pressure is above 14 gigapascals, it's already this tetragonal structure. But how to understand the different results from different techniques? Okay, we thought this question carefully, and some the structure were determined by synchronized X-ray diffraction or Raman scattering. Now they have different penetration depths. For synchronized X-ray diffraction, okay, the penetration depth is in micrometer length, but for Raman scattering, it's only 100 nanometers. That means, when we measure at the diamond navy cell, diamond navy cell, we have a big sample. The pressure will decrease. Okay, the hydrostatic pressure will decrease in the sample. The Raman only measure the outer shell of the sample. It's tetragonal because the pressure is higher. For X-ray diffraction, it measures the average of the whole sample or the inner side of the sample. So it's orthorhombic because the pressure is decreased in the inner side of the sample. So this picture can also explain why the superconducting volume fraction is low for single crystal samples. Okay, and the inhomogeneous pressure and its effect on superconductivity is further confirmed by a work from Norman Yau's group. Okay, so our conclusion is that I think our new understanding on the superconducting state is the tetragonal F4MMM structure. Okay, so here's a simple summary of my talk. So we found a superconductivity for this 1313 phase at 3.6 Kelvin, and neodymium and samarium doping enhances the interlayer magnetic exchange couplings and also enhances the TC. So the structure corresponding to the superconducting state of the bilayer 327 compound is the tetragonal phase. So in the end, I would like to acknowledge my students and colleagues. Okay, so that's all my talk. Thank you very much.
Thank you, man, for also perfect timing. All right. Any questions, comments? Let's see. Man, can you read John Mitchell's question from the chat?
I didn't hear any question.
No, so the question is in the chat. The question is in the 1313 material. Do you see any evidence for the density wave-like transition?
Oh, I think so. I think so. Let me show you here. As you can see here, actually, it's more obviously in these measurements. There are two anomalies. One, at different temperatures. I think they correspond to spin density wave transitions of the sample, but it's very complex. This is a 1313 phase. There is a single layer and trilayer. I think they may have different transitions for spin density wave and corresponding to different temperatures, but it need more diffraction measurements.
But maybe just to hijack John Mitchell's question. So, do you have like a quick summary of the nature of the density wave in general? Maybe both in the 327 bilayer and in general, whether it's spin, charge, both are mixed in.
Well, I think for the trilayer phase, it's people have a consistent conclusion. The trilayer, there are intertwined spin density wave and the charge density wave. Actually, it's proposed firstly proposed by John Mitchell's group. I think it's widely accepted. And recently, our collaborator Xinjiang Zhou's group they posted a paper on archive. I think it's yesterday. They propose it's Fermi nesting driven spin density wave. The data are perfect. And for the bilayer phase, I think it's the spin density wave or the magnetic order is very weak. It's I think it's also spin density wave or Fermi nesting driven. I think all itinerant electrons play a more important role.
Okay. But let's see. Next up, Han Hui Chen, please.
Oh, hi. Hi, Professor Wang. Yeah, so great talk. So I have a quick question. So you mentioned in your talk that the superconductivity exists in this high symmetry tetragonal phase. Then in the second part of the talk, you said that when you dope the samarium or neodymium, you can increase the superconducting TC. So my question is that how about the critical pressure? Does the critical pressure also increase with the samarium or neodymium doping?
Yes, but based on our standing, we doped different rare earth metals on this system. It seems crystal field do not affect the transition temperature. The lattice constant is is most important parameter for the
Yes, I
transition.
understand that. But my question is that the samarium and the neodymium have a smaller ionic size, so it will make the material more distorted. So in order to induce the
Yeah.
superconductivity, do you mean that you need a higher pressure in order to get
That's true. That's true.
That's true.
That's true. Yeah, that's
Okay.
true. As you can see here, for example, I didn't see. Let me see. Yeah, after we doped neodymium and samarium, we all need a higher pressure to induce superconductivity.
Okay.
Because
Okay. Got
there are more serious distortion for the structure.
Okay. Got it. Okay. Thank you.
I think George, do you have a question for
Yes,
Meng?
very nice talk. I was just wondering whether, there are two kinds of spin density or spin ordering temperatures or spin, because you can have a spin amplitude variation, as you do in the 113s, for example, and you can also have an ordering temperature of those spins, which have different sizes. Okay, so one is a spin ordering, and the other one is a real spin density. And the spin density generally is also related quite directly to the same Q vector as the charge density, if one has that kind of a problem, right? So there are actually both in the charge density, it should also have a spin density component, but then there can be an ordering temperature, which could be that these different spins are ferromagnetic or antiferromagnetic or whatever, stripy basis orderings. Is that so? One should be really a bit careful, I think, with the terminology of that. No.
Yeah, I fully agree with you. It's the magnetic structures is very complex in the nucleus. There are some neutron diffraction measurements proposed. Different moment sets on different nickel sets. So I didn't mention those work in this talk. Yeah.
But that could be happening here also, right?
Yes.
In
Right.
calculations that we've done on different kinds of magnetic order, one does indeed find that there can be very strong changes in the amplitudes of the spin, but also in the way that they order. Yeah.
Yes.
Okay, maybe I'll read off a question in the chat by Grace Pan, and unless Grace, you want to ask yourself.
Yeah, just a really quick question.
Yeah, please.
The discussion between the 1313 and the 2222 phases was very interesting. But at a very basic level, if you can just comment on how you synthetically favor that formation of the phase pure 2222 over the 1313.
What's the point? What's the key point of your question?
Do you have a control in the synthesis that
Exactly, yeah. How do you
good
synthetically favor the formation of one over the other?
That's a very good question. So honestly speaking, it's not very easy to control. So we repeat, we repeated the growth many times, but we found, at different part of the, single crystal, we can find different phases. Normally, the 1313 phase is in the end of the single crystal. Okay, only a small region has the 1313 phase, but the other part is a bilayer phase. So we need to characterize the samples very carefully. Okay. So that's all the information I can provide.
Okay, so you basically get a phase coexistence of both in most samples that you make, is what you're saying?
Well, actually, most of the samples is the bilayer phase. It's not easy to get this 1313 phase. But for some samples, in the end of the single crystal, we grow the samples with
the physical end. Okay.
In the end of the sample, we can find maybe millimeter-sized samples with this 1313 phase.
Okay, thank you.
Okay, maybe last question, Hua Zhou, please.
Oh, okay. It's a very quick question. So, very interesting about this SDW, the transition, because it does look like all the temperature you estimate the SDW is all based on the transport measurement, right? The kink on the RT curve. So I'm wondering after applied pressure, is that kink, when that kink disappear when you apply pressure, is that exactly the same time you're showing superconductivity? I mean, or there's still some overlap or some crossover, the kink. Yeah.
Okay. So first, for the bilayer phase, at the beginning we propose there may be spin density value and charge density value from the kink of resistance. But later on, there are many other groups measure the spin density value and the charge density value with different techniques. So the anomaly or kink on resistance indeed correspond to the spin density value transition. Okay, but for here, the 1.3 phase, we don't have the other measurements. We only have transport measurements. But when we increase pressure, they disappear. Okay, this we couldn't see very systematic evolution of the anomaly. Okay, we don't know whether they coexist with the superconductivity or they disappeared before the emergence of superconductivity. We don't know. Yeah.
Okay. Thank you.